combinations are just permutations, but now we're going to say that we don't care about the order of the objects. When we talked about repeated permutations, we pretended as though we could distinguish objects, and then we determined how many times we overcounted each permutation. Our goal here, we're going to do the same thing with combinations. We're going to pretend that order matters, and then we're going to determine how many times we overcounted because of this. So the answer is actually exactly the same as repeated permutations, but let's do an example to see that this is the case. Suppose that a restaurant offers 3 ice cream flavors, chocolate, vanilla, and strawberry. You're allowed to choose 2 of them, and you'll be served them in a bowl, and this ensures that order doesn't matter, unlike, say, a cone. How many different ice cream pairings are possible? Okay, so as I said, let's pretend that the order does matter, for which we know that there are 3 pick 2 or 6 possible pairings. Now I'm going to write them all down, ensuring that similar pairings occur in the same column. If we then say that order doesn't matter, well, each of these columns now represents a single pairing of flavors. There are 3 columns, hence 3 pairings. Okay, and again, just as with repeated permutations, we divide by the overcount to get the right number. Here, 6 represents the total ice cream pairings, assuming that order matters, while 2 is the number of times that we counted the same pairing once we decided that order no longer mattered. And we divide these numbers, and that gives us the total of 3 pairings. So to see how this generalized, let's expand the problem a little bit. We're going to add a 4th flavor, tiger tail. And we're going to assume now that let's pick 3 of the flavors to put into our bowl. Okay, so if order doesn't matter, there are 4 pick 3 or 24 options. I don't want to write them all down, so let's just take a look at the chocolate, vanilla, tiger tail representations. I'm going to write them all down here for you to see, and if we count them, we see there are 6 permutations, and all of these are going to count as a single CVT option once we say that order doesn't matter. So since there was nothing special about the choice of CVT, this is going to happen in every selection of 3 flavors. And from that, we can then conclude that there are 4 pick 3 over 3 pick 3, which works out to 4 different possible flavor combinations. So what we've learned is that if we have n distinct objects, then the number of k combinations, which we write nck like this, is the number of k permutations divided by the number of ways of ordering those permutations. Okay, and this is going to ensure that we've removed the restriction that order matters. Let's do one more example to solidify this. So let's suppose that 8 points are drawn on a piece of paper, and that no 3 of these points lie on the same line. If we make triangles by choosing the vertices to be, one of these points on the paper, how many triangles can we make? Okay, so the condition that no 3 points lie on the same line, that just guarantees that any of these 3 choice of points actually creates a rectangle. So don't worry too much about it. Let's start out by drawing a typical example of 8 points. And it's going to help if we label them. So let's do that like so. If I draw a triangle like this, okay, I'm going to say that this is the triangle 2, 3, 5, so that it's labeled after its vertices. And we can see that here that order doesn't matter. So triangle 3, 2, 5, for example, is exactly the same. Thus, the number of triangles is just the number of ways of choosing 3 vertices from these 8 points, and that gives us 8 choose 3 triangles.